Hello everyone and welcome to the video. Today I'll be exploring a very cool math module called SymPy. Now SymPy is used for symbolic mathematics, meaning it can do many things like algebraic manipulation, it can do matrix manipulation, it is used in calculus, things like integrating, finding derivatives, and many more actually. You can check the documentation if you would like to know everything that SymPy does. But today I'll be limiting the scope of the video of only checking out what cool functions it has to solve number theory problems. Now, if you don't have SymPy downloaded already on your computer, you can use Pip Install. Just copy this line and paste on your command prompt. Or if you have Anaconda, you can go to the Anaconda prompt and use this line to download the package. Now, it is one of the main packages that comes with Anaconda, so if you've downloaded Anaconda recently, you have no need of using this line, but maybe if you downloaded Anaconda a while back, you might have to update so you can get all of the newer version features of SymPy. Now that you hopefully have SymPy installed on your device, we'll be importing from the ntheory file in the SymPy module, so from sympy.ntheory, and then we'll be importing all of these functions. Now these are not all of the functions that the ntheory file contains, but these are the ones that I felt will be used most often by people. Now first off, let's explore these three functions: prime factors, divisors, and factor int. Now the three of them basically do the same thing, which is finding the factors, but they do it in different ways that we're about to figure out. Now let's use these three functions to factor the same number. Let's say negative 63. Okay, so first off, let's use prime factors to factor negative 63. Now let's copy this. Okay, now the second time we'll be using the divisors function. The third time we'll be using the factor int function, just so we can see what are the differences in these three functions. Now, the prime factors got us only the positive integer prime factors of the number. So negative 1 was excluded, but it's actually one of the factors because it will only give back positive prime integers. The divisors function gave back all of the numbers, even the composite ones like 21 and 9, because any number, any positive integer that divides this number will be included in the returned list that divisors will give back to you. Now factor int will give you the factors and to what power each of the factors should be raised so that you get the number. So you have negative 1 to the power of 1, 7 to the power of 1, and 3 to the power of 2, and these all multiplied together will give you back negative 63. So this is kind of the prime factorization as you used to do it in school. Now for the isPrime function, it does exactly what it says. You input a number as an argument, a number n, and it returns true if that number is prime, false if it's not. So let's test it for the number 63. Okay, just let's remove the negative. Say is prime. As you can see, it returned false. Now let's use it for the number 23 maybe. And it is true because this number is actually prime. Divisor count will give you how many divisors a particular number has. So it's equivalent to actually finding out the length of the list of the divisors output. So for the number 63, let's say divisor count will give us back 6, which is the number of divisors for 63. Now let's check out this cool function prime. Now prime will return the ith prime number. So if we give it prime 1, it'll give us back the very first prime number, which is 2. If you go for the second, it'll give us the 3, which is the second prime number. and so on. Prime pi will give us the number of prime numbers up to and including a number n. So to illustrate what prime pi does, let's say prime pi of 13. Now what this function will be doing is give us the number of prime numbers that is less than or equal to 13. So that would be 6, which are the 2, 3, 5, the 7, the 11, and the 13, because it's up to and equal. The next prime function will give us the prime number that comes exactly after 13, and that would be 17. But this function can actually take more than one input, so we can say what is the second prime number bigger than 13, and that would be 19, which makes sense because 18 is not prime. Previous prime does the exact opposite of next prime, so the previous prime to 13 would be 11. Prime range will give us the all of the prime numbers that exist in a particular period. So let's say prime range of all the primes that come between, let's say, 10 and 40. So now it'll return to us a list with all the prime numbers in this period. Give us back a generator. Oh, okay, so it gave us back an object, so we'll go list prime range, and there we go. These are all the prime numbers in this range. Now for rand prime, it will pick a random prime in a particular period. So if we're using the same period, the numbers between 10 and 40, let's go for rand prime. Let's see which random number it picks. Int object is not, oh, okay. Let's remove list, we have no longer use for that. 37, let's use it another time, we'll get 29, another time we'll get 23, and so on. Composite is very similar to prime, but instead of counting the ith prime, it will be counting the ith composite. Let's try that out. Composite. Let's see, what is the third composite number? And that would be 8, exactly what we expect. And composite pi is also very similar to prime pi, but it will be counting to the number of composite numbers up and including a particular number. Now let's check out the digits function. Now what the digits function does is you actually input as argument a particular number. Let's choose the number 1, 2, 3, 4, 5, 6, 7. And what this function does is return to us a list with each one of those digits as the elements of this list. So it starts out from left to right, 1, 2, 3, 4, 5, 6, 7, and the first number will be what base is this number, and this function defaults to 10, but you can actually input as a second argument, let's say b equals 2. It will convert this number to base 2, which is binary, and then it will give you back the list of the digits that number should have. And there you go. The first element was 2, telling us this is base 2, and these are the digits of the converted version of this number to binary. Now the function prime and u does something very similar to divisor count, but actually with prime factors. So it'll be counting the number of prime factors that a number n has, as opposed to divisor count that did the same with divisors. So to illustrate this, let's say prime and u. Let's use it with the number, let's say 63, the same number we had. So prime and u of 63 will be 2, because the only distinct prime factors it has will be 3 and 7, because it's 9 times 7, but 9 is composite. and the number itself 63 is also composite, so it won't be taken into account. So bear in mind these differences between the different factoring functions when you're about to use them, and they're all useful, depends on what you're using them for exactly. Okay, let's check out the count digits number. Now actually this function is very cool. Let's say count digits. Okay, what this function does is that it will give you back the number of how many times have you used a single digit. So how many ones are in this number, how many twos are in this number, how many threes, how many fours, and so on. So it'll return a dictionary containing how many of all of these different digits do you have. So there's 2 ones, okay, there's 2 twos, there's 2 threes, and 1 4. If you wish to print it out, you can convert this to a dictionary so you can get a nicer output. Oops, what did I do? Okay, only these, let's go. And there we go, there we have it as a dictionary. Now let's check out the nPartitions function. Now if you don't know what a partition is, a partition is how many ways can you represent a particular number as a sum of positive integers. So if you bear in mind the number 3, you can represent the number 3 as 3, or maybe you can say 2 plus 1, or maybe you can say 1 plus 1 plus 1. And these are all the unique ways that you can represent the number 3. Now in partitions, what it does is give you how many partition representations could there be of a particular number n. Now it doesn't have to be a number. This function can be used for any set when you are considering the number of partitions a set could have. The only relevant kind of factor to consider is how many elements are there in a set. So in any set with 3 elements should have the same kind of partitions. Okay, now let's check out the function on the same number we just illustrated, the number of partitions for. Let's say n partitions for the number 3. You should expect to have 3. The n-order function is used to find the order between 2 numbers. Now if you pick any 2 numbers, let's say a and b, what is the power that if you raise a to, you should have a remainder of 1 mod b. Okay, so the n-order function is used to find the power. That will give you a remainder of 1 if 1 is raised to this power and then calculated modulo the second number. So let's use the n-order function. Okay, let's say we wish to find the order between the 2 numbers 3 and 5. Okay, let's calculate, and that would be 4. Let's try that out. If you actually print, let's say 3 to the power of 4 modulo, let's say we set the number 5, right? And there we go, we get a remainder of 1. So 4 is the order of 3 and 5. Now that should be it for today's video. If you guys liked the video, please hit that like button, and don't hesitate if you have any questions for me or have any suggestions for this channel. Thank you for watching.